Welcome to The Explainer. Today, we're diving into a really fascinating theoretical study that asks a pretty radical question. What if we could navigate the world of information not like a flat map, but like a universe with its own kind of gravity? So, everything we're about to talk about is based on a theoretical paper by the researcher Mohammed Ben Ammar Charaidi. This work lays out a completely new mathematical framework for how we find information. We've put the paper's DOI right there on the screen so you can check out the source for yourself. All right, here's how we're going to break this down. First, we'll look at what's wrong with search right now. Then, we'll borrow a huge idea from physics. After that, we'll get into the GRAVITAS framework itself, what it could be used for, and what the future holds. So let's start with the big question. Why do we even need a new way to search for things? Well, for more than 50 years, from the simplest models to today's huge neural networks, we've basically treated the world of information as if it's completely flat and uniform. You've probably felt this, right? You search for Apple and you get this weird mix of results about fruit and the tech company, even though all your recent searches have been about pie recipes. That's a classic symptom of this flatness. Real knowledge isn't like that. Some topics are like bustling cities, dense and interconnected, while others are like empty deserts between them. A flat geometry just can't see the difference. And that really brings us to the core problem here. Current models, they just force a fixed, flat grid onto all of information. But the paper argues that what we really need is the exact opposite, a dynamic, curved geometry that actually bends and adapts based on the density of the information it's mapping. So where do you get an idea like that? Well, the inspiration for this new geometry comes from one of the most brilliant scientific theories ever developed. In Einstein's general relativity, you have these massive objects, like stars and planets, and they literally bend the fabric of space-time around them. That curvature then tells other objects, like comets or light beams, how to move. It's this beautiful two-way street. Matter tells space how to curve, and space tells matter how to move. And this quote just nails the core idea of gravitas. The proposal is to use that same exact logic for information. So really dense topics, these semantic hotspots, they would create a kind of semantic gravity, bending the information space and guiding our searches along these new curved paths. So, okay, let's formally introduce the star of our show, gravitas. It's actually an acronym, and it stands for Geometric Retrieval via Adaptive Tensorial Information Density Attractors in Semantic Space. A bit of a mouthful, but the name says it all. So let's just hammer this home, because it's the key idea. It is a direct parallel. Just like mass curves space-time, dense pockets of meaning curve information space. And that curvature, it creates the most natural paths. Think of them like valleys carved by a river that lead you to the most relevant results. These paths are called geodesics. So how does this whole thing actually work, mathematically? Well, it rests on three main pillars. First, there's the semantic manifold, which is basically the flexible, curved space where information lives. Second, you have the gravitas field equations, which are the rules that say exactly how information density bends that space. And third, there's geodesic retrieval, the totally new method for actually navigating these curved paths. Now, the paper is really clear on this point, and it's a super important one. This is a mathematical analogy, not a literal physical theory. We're talking about a Riemannian geometry, which is a geometry of space, not space-time. There's no time dimension, no light cones, none of that. This is all about mapping the shape of ideas, not the physics of the universe. Okay, so we've got the theory, but what does this actually mean for, finding stuff? Well, it completely changes how a search query gets from point A to point B. So instead of your search just being a straight line, it becomes what's called a geodesic trajectory. So let's go back to that Apple search. Now, your query isn't just floating in a flat, empty space. It's actually pulled by the semantic gravity of all those baking and fruit topics you've been interested in. It gets pulled into the orbit of the most relevant cluster of ideas, and it finds a much better destination. This also creates a totally new way to rank results, and it's called geodesic relevance. See, the best result might not be the one that looks closest to your query at first glance. Instead, it's the one you arrive at after your search has traveled along the natural contours of the knowledge landscape. It's a system that finds documents that are truly at the heart of a topic, not just the ones that have a few similar keywords. And here is where things get really, really cool. The most powerful part about this framework is that it's not just about building a better search engine. Not at all. It's a universal concept. I mean, just look at this list. The paper outlines this incredible range of fields where this could be a total game changer. For example, in drug discovery, it could help find molecules that look really different but have similar effects by navigating the geometry of chemical properties. In neuroscience, it might even help us model the actual shape of our thoughts by mapping how concepts are clustered in the brain. Basically, anywhere you have complex, dense data, this geometric approach could unlock some powerful new insights. And to make sense of all these different possibilities, the author organizes them into 3 tiers. This is a way of classifying them based on how directly the mathematical analogy applies, from a perfect one-to-one fit all the way to more exploratory what-if kinds of ideas. It shows this isn't just a random wish list, but a really structured and thoughtful research program. So, what's next for such an ambitious idea? It's a great question, and it's really important to be clear about what stage this research is at right now. Okay, so GRAVITAS is first and foremost a theoretical study. It's that essential first step. It lays out all the math, it proves that it's all internally consistent, and it even proposes a detailed plan for how to test these ideas against real-world data in the future. And like any truly groundbreaking theory, it doesn't just answer questions, it opens up a ton of new, fascinating ones for mathematicians to tackle. I mean, these problems here look complex, but they boil down to some really cool goals. Can we map the entire shape of an information universe? And can we predict how that map is going to change as new knowledge is added every single day? And that leaves us with a final, pretty mind-bending thought. If we have the tools to actually map the shape and curvature of information itself, then Gravitas isn't just giving us a better search engine, it's giving us a whole new lens to understand knowledge itself.